Welcome to a SimCenter AimSim Student Edition tutorial solving a problem of machine dynamics and vibrations. The problem statement for the series has been constant, but with the goals for this part being how to solve two-body dynamic problems in AimSim and utilizing the modal shape feature within linear analysis. This is part 4 of the series, which is how do the additions of a wheel and tire affect the model, and how fast does the trailer need to travel to excite its resonance frequency if there is a bump every 5 meters. Sketching the model will begin similarly to the model in part 1, with a mass connected to a spring and damper on one side, and a zero force source on the other. For the remaining port of the spring and damper, attach a mass component for the combined wheel and tire. Next, place a spring underneath this to replicate the stiffness in both tires. Lastly, close the remaining port of the spring with a zero-speed source. This model is built to combine the properties of the two suspensions, wheels, and tires to create a two-body dynamics problem. Moving to submodel mode, Premiere Submodel is acceptable. The parameters for the top mass and the spring and damper components will be the same as what was done for the model with a combined suspension, using the global parameters whose values were determined in parts 1 and 2. Adding two new global parameters, the combined mass of one wheel and tire is on average of 50 kilograms, and the tire stiffness is found to be 300 kilonewtons per meter. The mass value within the component can be set to the new global parameter times 2, and the same can be done with the stiffness within the spring component. Also within the mass, be sure to change the inclination angle to -90, like the trailer mass, so its displacement is vertical. Looking at the problem mathematically, the system has 2 degrees of freedom. Each mass has respective forces moving on it, with the wheel mass experiencing force from the tire stiffness, suspension stiffness, and suspension damper. The trailer mass is experiencing forces from both the suspension stiffness and damper. Using Newton's second law with no forces acting on the system, equations of motion for each mass can be found. These equations can be rewritten into matrices that correspond to the mass, damping, and stiffness. Utilizing these matrices, eigenvalues can be found as the determinant of the matrix operation shown, which when solved, provides the results shown with a real and imaginary component to the frequency. To find the correct value for this frequency, take the root of the squared sums of the real and imaginary components, which will be in radians per second. And after dividing by 2 pi, the values for natural frequency can be shown in hertz. Back in AimSim, move to simulation mode and enable the linear analysis option and add a linearization time of 10 seconds, and run the simulation. Once complete, open the Eigenvalues menu within the linear analysis dropdown. The two frequencies value, real components, and imaginary components are equal to what was calculated. Now, let's expand the model to have a suspension, wheel, and tire component for each side of the trailer. The model is now expanded to have a suspension and wheel for both sides of the trailer. The total values for the suspension stiffness and damper divided between the two, and the mass and stiffness from the wheel and tires are applied appropriately. Performing another simulation, reopen the eigenvalues once complete. The two previous values are present, but with a third as well, which can be attributed to the discretization of the model. To grasp a better understanding of what is causing the third value, the modal shapes feature can be utilized. To begin for each of the variables for the mass components, change the status for the displacement by double-clicking in the column and changing it to a state observer, and then rerun the simulation. After completion, open the Modal Shapes menu from the dropdown. Change the linearization time to 10 seconds. All of the eigenvalues are available within the frequency dropdown menu. The observer list below has each of the variables' displacements mentioned prior. Selecting on one from the list will highlight its corresponding component within the model. Each variable can be displayed as a plot to see the change in magnitude across the simulation. To do this for the first frequency, select all the masses and press plot. a new window will appear, and when pressing play, 3 bars corresponding to each of the masses will move, showing their behavior with them all oscillating together before being damped out. Closing this and moving to the second frequency, which was calculated prior, 15.78 Hz. Each of the wheel masses are oscillating together, with the trailer mass moving opposite. For the new frequency of 15.85 Hz, the modal analysis plot shows the wheel masses having oscillations that are directly opposite each other, which would have not been possible when simulating the wheels as one mass. With each of the resonance frequencies analyzed, let's take the smallest value of 2.46 Hz as the goal for the trailer to oscillate at for the second portion of the video. In order to simulate the trailer traveling over a bump in the road, replace the zero-speed source with a converter of linear displacement and velocity, with an input signal for the displacement. The input source will be in the form of a square wave function. For the new components, Premiere submodel is acceptable. For the parameters of the square wave, the frequency will be the natural frequency of 2.46 Hz, with a pulse ratio of 10, a minimum level of 0, and a maximum level of 0.01. This makes it so that the trailer will travel over a quick small bump appearing at its resonance frequency. Moving to simulation mode and performing one simulation, and displaying the mass displacement plot, shows how the mass oscillates at its resonance frequency, being excited by the square wave function simulating these bumps. Knowing that a bump needs to occur every 5 meters at a frequency of 2.46 Hz, converting this frequency to a time of 0.4065 seconds, and dividing this distance by time, the required velocity to excite the trailer at resonance frequency would be 12.3 meters per second. And this concludes part 4 and the final part of this tutorial series. Thank you.